Hello, my name is Rafael Weilharter from the Institute of Computer Graphics and Vision at the Technical University of Graz in Austria. I'm going to talk about our paper titled Hammer, Learning Entropy Maps to Create Accurate 3D Models in Multi-View Stereo. First off, I want to quickly talk about the motivation for this work. In multi-view stereo, we aim to generate a dense 3D model from a series of 2D images. State-of-the-art methods treat this as a classification or regression problem and estimate depth maps with deep neural networks. Despite the fact that the output is first a depth map, the most common benchmarks today only evaluate point clouds instead of depth maps. This is why we need to find a way that can accurately project 3D points from these 2D maps. An additional challenge is posed by the memory requirements of the network. When dealing with images of HD quality, many networks are quickly brought to their knees. The main contributions of our work can be summarized as follows. We will propose to learn filter masks in addition to depth maps via entropy loss. I will go into more details about this later. With these learned filter masks, we enable the use of fixed fusion parameters for different scenes. This has been a long-standing problem in multi-view stereo, where the fusion step usually requires a tedious manual parameter search. To tackle the problem of high GPU requirements, we implemented an adjustable interval parameter which scales the network's depth resolution independently of memory. Furthermore, we introduce randomized matched patches for the training phase. This allows us to use the full resolution of any available dataset without removing information by resizing images. We can see this approach depicted in the image here. The red square indicates the naive solution to select patches where we just choose the same area in all our multi-view images. This can lead to the problem that there is not enough overlap between patches, and the network is unable to estimate the corresponding depth. In contrast to that, we project several points, shown here as red crosses, into the neighboring views, and then choose a patch corresponding to the centroid. This guarantees enough overlap for the reference view. Our proposed solution to the multi-view stereo problem is titled Hammer, which stands for Hierarchical and Memory-efficient MVSNet with Entropy-filtered Reconstructions. The illustration shows a comparison of network outputs for different state-of-the-art methods on the family scene of the tanks and temples dataset. We can see that our network is able to produce very smooth depth maps, while other networks struggle with noise, especially in the background. Here we have an overview of our network. To train the network, we first extract features from the input image in a unit fashion at 5 different resolutions and use the homography warping to assemble a 3-dimensional cost volume. For each feature stage, we assemble the cost volume twice with different depth resolutions. The cost volumes are regularized via 3D convolutions, and via regression we obtain a depth map. As many other networks, we use the coarse depth estimate to initialize the values for the next stage. In the final regularization stage, we add an additional network branch that outputs the entropy values for each depth estimate. We apply a depth loss in every stage, and for the last stage, we add an entropy loss. As our network is trained via regression rather than classification, there is no guarantee that entropy is low for good depth estimates. This is due to the fact that a good depth estimate could also be achieved by an equal distribution of probabilities, which is just treated as a different weight in regression. However, we want to encourage the network to apply a single strong probability to the correct depth estimate, bringing this approach closer to a classification task. In order to enforce a low entropy on a correct depth estimate, we apply an additional loss between entropy and the depth error map, as depicted here. What this means is simply that we reward either a good depth estimate with a low entropy or a bad depth estimate with a high entropy. And here we can see the effect of this entropy loss. On the top we have our baseline network trained without the entropy loss. We obtain the entropy map naturally from regression probabilities. On the bottom we use the separate entropy map output of Hammer. While quantitatively the raw depth output has already improved in Hammer, it is hard to tell from the images alone. However, when combining the depth with the thresholded mask obtained from the entropy, we achieve a very clear improvement in the output. We evaluate Hammer on different benchmarks, and first up we compare our results on the TTU benchmark to traditional and recent learning-based methods. The average distance for every estimated 3D point from a ground truth point is reflected in the accuracy score. If we go in the other direction, meaning the average distance for every ground truth 3D point from the generated point, we can obtain the completeness score. The overall score reflects the mean between the two. On top, we have two traditional methods with Geboomer and CalMap, and the rest of the methods are learning-based. Our approach demonstrates great performance, only being surpassed by the recently released GeoMVSNet. While it is widely accepted in common practice that the same fusion parameter settings are used for the whole dataset on DTU, this is not applied for the tanks and temples data. We argue that for a fair network comparison, fusion parameters should stay at a constant setting. Therefore, we compare Hammer to high-performing methods on the benchmark when settings are kept consistent throughout the dataset. We can see that our approach performs exceptionally well without the need to change the fusion settings from the DTU evaluation. And while our F-score numbers on the official benchmark might be a bit lower than, for example, GeoMVSNet, we can see a clear qualitative advantage of our method here. This graphic depicts the precision and recall values for every point in the generated 3D model. Our method is able to precisely filter out any outliers due to the filter masks obtained from Entropy. So to sum up, we have proposed Hammer, a deep neural network that is able to produce precise filter masks alongside accurate depth maps. Our novel entropy loss improves the depth map output of the network while also providing the required entropy map to filter out points before the fusion stage. Hammer can be trained on an almost arbitrary depth resolution that is independent of GPU memory. Moreover, by using randomized matched patches in the training phase, we are able to train our network on small patches, which leads to a very low memory requirement for training. Besides that, the main advantage of our method is that we eliminate the need of tuning fusion parameters to create a 3D model from its depth maps. We confirm the strong performance by evaluating with fixed fusion parameters on the very different benchmark scenes for DTU, tanks and temples intermediate and tanks and temples advanced. Thank you very much for your attention.